Alright, today we're talking about Chapter 5, Section 3, the properties of logarithms. We are going to be doing the algebra of them now. Alrighty, so starting from the top. In this section, we learn how to manipulate logarithmic expressions using properties of logarithms. Understanding how to use these properties will help us solve exponential and logarithmic equations that are encountered in the next section. Recall from section 5.3, that's this section. Well, it's hard to recall from this own section, huh? Anyways, the general properties and cancellation properties of logarithms. We now look at 3 additional properties of logarithms. All right, in one moment, my cat wants up. He's like you guys, he doesn't want to even hear about math. All right. So, properties of logarithms. Starting here. All right, so if we have some b greater than 0, which we have to, we have that base greater than 0, and if the base is not equal to 1, and u and v represent positive numbers and r is any real number. Okay, again, this is just sets the groundwork of what we're allowed to use. That's really it. Okay, so if we have the log of some base, and we are multiplying 2 separate numbers, then we can expand those two by, I guess it'd be by factoring there, but we can expand log base b of uv, we can expand it to log base b of u, and then plus log base b of v. Okay, so if we are multiplying, then we have that, then we have the addition sign. Okay. And then, of course, if we are dividing, okay, if we have some u over v, if we're dividing, then we're going to be using the subtraction sign. Okay. And then lastly would be the power rule, and it's kind of similar to something you might encounter in calculus. It's not calculus, obviously, but in calculus, what you do is you deal with moving your exponent down to the front. Obviously, you subtract one, all that good stuff if you have taken calculus. But it's really just the steps, right? What you're going to do here is if we have log base b of some base, if we have log base b, and then of some u raised to the r power, doesn't matter what it is, then what we can do is we can put that r out front. Of course, that's what we see here. Okay. So again, I know these letters don't mean too much to you. Well, let's continue on and read the paragraph real quick first. So to prove the product rule and quotient rules of logarithms, we use properties of exponents and the method of relating bases to solve exponential equations. The power rule for logarithms is a direct result of the product rule. You can click on that video if you want to. We can't, obviously. All right, anyways, so again, what I was going to say was we don't really care too much about words and letters, right? We want to get to the meat of this, don't we? Let's begin. All right, so today I think it's only 18 pages, but there's a lot of computation involved here. So that might go by quick, but it's going to have to be, you got to keep up. All right, so we need to, this says, or reads, use the product rule for logarithms to expand each expression. Okay, so A, we need to expand that expression. Notice that we have, oh, something I should have said. And of course, if we have the equal sign here, we know that going from left to right is the same thing as going from right to left. Okay, we know that they are equal to one another. For example, 1 we're going to be expanding. We're going to be going from the left to right part, right? But here in a moment we're going to be condensing, going from right to left. Okay, anyways, so yes, we're expanding here, and notice how it's 5x. That is essentially 5 times x, right? So we would say natural log of 5 plus, because it is a multiplication, natural log of x. And that's it. Pretty easy. And then b would be the log base 2. Okay, and this is also a multiplication, so it's going to be log base 2 of 8 plus log base 2 of x. Okay, we're not done yet though, because log base 2 of 8, that is actually a number, isn't it? Right? 2 raised to what power will give me 8? Well, that would be 3. So this is essentially saying 3 plus the log base 2 of x. Okay, and I'm pretty sure I guess we're going to go into the quotient rule next, right? So we're probably going to expand into the quotient rule for the next example. Yep. Alrighty, excuse me. So use the quotient rule. All right, and again, we're just going to expand these. So we're dividing here. The argument is being divided, so we know we're going to use a subtraction sign. So we're going to say log, looks like lag, doesn't it? Log base 5 of 12. Okay, and then it's going to be minus log base 5 of x. And that's pretty easy. That's it, right? Again, it's division, so we just subtract. B, we're going to have the, oh, well, this is a good one. So we're going to have the natural log of x minus the natural log of e to the 5th. Okay. So recall on the previous page that if we have the the first page, I guess, if we have that exponent here, we'll put it out front. Okay. So we could essentially rewrite this as the natural log of x minus 5 times the natural log of e. Okay. Well, we talked about in the previous section that the natural log of e, well, that's just 1, right? So this is the same thing as saying the natural log of x minus 5, right? Because this is just, that's 1, and 5 times 1, right? Right, so that is that. And actually, I'm going to go ahead and keep that there. And I guess we're going to go to the exponents now. Or the power rule, sorry. The power rule. Alrighty, excuse me. So we essentially use the power rule on the previous page. I guess we're going to talk more about it now. Alright, so we're going to put this exponent right here. We're going to put it out in front. Okay, so this is going to end up being, looks like 3 log of 6. And there's nothing we can really do about that, and we're done. Nothing more, rather. Okay, and then B. All right, so B, let's go ahead and rewrite this. Let's take care of this radical. Let's go ahead and rewrite this as x to the 1/4 power. Now, you don't necessarily have to rewrite it like this, you know, because I mean, at this point you probably have a good understanding of exponents. But I'm going to do it just to be abundantly clear. Okay, and we know that that is the same thing as, we're going to put that exponent out front, 1/4 log of 1/2 of x. Okay, and that's that. Okay, so here's something, I don't know if we actually touch on it, so I'll say it for if we don't talk about it. But again, in pre-calculus is basically just taking everything that you did in Algebra Essentials and College Algebra and wrapping it up into a turbo boost, a lot harder problems of a class. Okay, so if you want more material for this particular stuff, like the thing we're called properties of logarithms. Yeah, properties of logarithms up here. Just look at the title. Then look for that similar title in my pre-calculus playlist, and you should be just fine. Okay. But anyways, I think that covers A and B there. Okay, it actually does cover it here. It covers it right here, what I was going to say. So that's good. Let's put that here on the current page. Okay, so it does cover it. Notice it says caution. log base b of u, if the entire thing is raised to some r power, okay, then that is not equivalent to what we're doing right now. That exponent must be on the argument, right? It must be on the argument here. And of course, you see up here, must be on the argument. Okay. If we are taking the powers of the logarithms, for instance, if let's look at a here, because I'm pretty sure you might have a problem like this in your text. If it was log of 6 cubed, okay, that is not going to be 3 log 6. Okay, and instead, what that is log of 6 times log of 6 times log of 6, right? Of course, the way we do our exponents, right? So that caution is there. I just almost missed it. All right, now I think we can move on. All right, so, excuse me. We're going to use properties of logarithms to evaluate each expression without using a calculator. Okay, no calculator needed, right? Because we've seen these kind of problems before, and so this is 7 raised to this. Actually, we're going to probably move that down a tad. This might be a 2-pager. It's going to be 7 raised to the. Okay, so we have the same base in my numerator. All right, so this it's an addition problem here. So we know that in order to combine them, we have to multiply my two arguments, which are 6 and 3. So we're going to say 7 raised to the log base 7 of 18. Okay. Now we've seen this before. If we have some number raised to the log of that number, and then the argument being 18, then we know, and this is like, it was a cancellation property we did on the previous section. Then we know that my solution is going to be my argument 18. Okay, let me see if I can think of another way I can put that. Let's see if we did. Okay. Here's another way to think about it if you forgot about the cancellation properties. Okay. Because I know I said, I don't necessarily remember them. It's just they come to me, right? So let's go ahead and if we were to take this, actually, just this left side, just the left side, and we were to put it into logarithmic, the logarithmic form, going from exponent to logarithmic, right? Then this would be log base 7 of what? Of what? What is my argument? Okay, well, I don't know what my argument is, right? Because we don't know what it's equal to yet. And that's going to be equal to my exponent, which is log base 7 of 18. Okay, and then notice how, if we have log base 7 on the left, log base 7 on the right, then we just simply have to equate my arguments, so x would be equal to 18, so that's where we get 18 here. Okay, and again, I feel like I might have hand waved that a little bit, so let me explain this a little bit more. We know that if we have e to the x is equal to some y. Okay, that's essentially what we did here. We e to the x, well no, sorry, that's what we're doing here. Okay, and then we know that we can change that from e to the x. I should have done e. Let's do b. Sorry, this might be one of those cases where I over-explain, but whatever. It's better under-explaining, am I right? All right, and we know that is the same thing as saying log base b of y is equal to some x. Okay, we did that on the previous section. Remember, I color coordinated those. That's essentially how we get this 18. Okay, if you don't want to remember that cancellation property, which I told you you don't have to, but once you see it enough, you're gonna be, oh, this is 7 raised to log base 7 of 18. Okay, so the answer is 18. Okay, once you see it enough, it'll come to you. But if you want to see why that is from using the cancellation property, again, I just took what's in blue up here, and I put it into logarithmic down here, log base 7 of x, and then I equated x and 18. And I got lines everywhere, and I know for a fact I probably over-explained it, so we are done with this, with A. Okay, excuse me. Now B. We're going to have, all right, so this is, we got a subtraction and an addition. A nice addition though. Okay, so let's go ahead and start this. So we can write this as e to the, and it looks like the 2's in front, so we can say the natural log of, we're going to go ahead and write 25. Okay, why are we going to go ahead and write 25? Well, we know that if we were just to look at this, 2 natural log 5, if we were just looking at that problem, we know that we put the 2 onto the 5 as an exponent, and it'd be 5 squared, which is 25, and that's why I went ahead and wrote 25 there. Okay, and then it's going to be, it's a minus the natural log of 64 raised to the 1/3, which we know that would be the cube root, but we'll keep that there for right now. Same thing though, we're going to, again, this 1/3 up here goes on the exponent of 64. Now really quickly, if you were to get your calculators out, and if you took the natural log of 1, you would get 0. So this natural log of 1 is essentially just 0, right? So we can just leave that alone, right? We don't have to write plus 0, do we? No, because that'd just be dumb. We could write plus 0 to everything, couldn't we? I'm 33 plus 0 years old. That's a dumb thing to say. But anyways, so that's what we have. And for the sake of this, let's go ahead and, so I can have a little bit of space here, let's go ahead and rewrite the, let's go ahead and rewrite 64 to the 1/3 power. Let's rewrite that as the cube root of 64 real fast. Okay. All right, so now that we have that, all right, so we have e to the natural log of 25. Actually, let's not do that just yet. No, it wouldn't matter. Okay, we'll write to the natural log. Okay. All right, so we have a subtraction here. Let's just look right here. It's a subtraction sign, so we know it's going to be, we're going to turn this, when we condense this, we're going to turn it into a division, right? So turning this into a division, it's going to end up being, okay, so, well, what is the cube root of 64? Well, that's going to be 4. So it's going to end up looking like the natural log of 25 over 4, right? We have that subtraction sign there, so that's why we have a division. So it's going to end up being the natural log of 25 over 4. So we're going to have 25 over 4. Alrighty. Well, we know that e raised to the natural log, right? E to the natural log is just 1. Okay, so this means that this solution is simply 25 to the 4th. Okay, similar to how we saw in the previous example where we took 7 raised to log base 7, it just becomes the argument. Same thing here, e raised to the natural log, and it just becomes the argument. Okay. So anyways, hopefully I didn't over explain that or confuse you, but that's the way you do it. Okay, so we have been condensing, so now we need to expand. And we will keep that paragraph in there. So sometimes it is necessary to combine several properties of logarithms to expand a logarithmic expression into the sum and or difference of logarithms, or to condense several logarithms into a single logarithm. Now we're going to be expanding. So this probably looks like a 2-pager, so I'm not going to go too crazy here. All right, so we've got log base 7. Okay, so we've got a 49 times x cubed times the 5th root of y squared. So this is going to be 3 terms. Okay, so let's just go ahead and begin. We're going to have log base 7 of 49. Okay, so that's nice and convenient. That's going to actually be a number, right? Because 7 squared is 49. So this is going to end up being 2 when we clean it up. And then we're going to say plus log base 7 of x cubed and then we're going to say plus log base 7 of the 5th root of y squared. But let's go ahead and write that as y to the 2/5 power. All right, now we're going to clean this up. All right, and I said earlier that log base 7 of 49, that is 2, again, because 7 squared is 49, so we're going to say 2, and then we're going to say plus, and we're going to put that 3 out front, log base 7 of x, and then we're going to say plus 2/5 log base 7 of y. Okay, so I do remember saying at the beginning of this chapter, I said something like along the lines of, okay, so this chapter, it's not so much mindless computation that we've done before, right? Instead of factoring our brains out, it's actually just going to be a lot of moving stuff around. And this is a prime example. We just moved a lot of stuff around. Obviously, we had to compute that log base 7 of 49 is 2, but other than that, we just have to move things around. Okay, B, excuse me, B. We have a division, so this is going to be subtraction signs. So let's go ahead and start on this. Actually, before we go ahead and start on this, let's actually take a look at the numerator here and notice that it is a difference of squares. Okay. No, let's not look at that just yet. Okay, let's go ahead and rewrite. Let's go ahead and write this as a expanding it first. So we're going to say natural log of x squared minus 4. Okay, but we know it's a difference of squares, and we're going to have to come back to it. Okay, then we're going to say minus the natural log of 9. Oh gosh, e raised to the x cubed power. Perfect. This is going to be nice and beautiful. Okay, so here's what we're going to do. On the left side, we see that it's x squared minus 4. So we're wanting to expand this completely. It says as much as possible. Okay. So what we can do is we can rewrite this now as the natural log of, and it's going to be x plus 2, x minus 2. Okay. And I have been asked before, how do I know when to use a bracket and when to use a parentheses? And realistically, it's just you use one or the other, or use them both when just to make things easier on the eyeballs, right? I mean, there's not a problem in the world to put a parentheses and parentheses. There's nothing wrong with that. I just prefer to make things look a little bit nicer like this. Anyways, and then minus. It looks like we can pull that. Oh no, I didn't even expand that all the way. Let's before we get too far here, let's go ahead and expand this all the way. All right, because it is a 9 times e raised to the x cubed power, right? So that tells me that we're going to end up having 2 of those. Okay, so we're going to say minus, and we're going to put this in a bracket, minus the natural log of 9, and it's going to be plus the natural log of e raised to the x cubed. Okay. All right. Well, it's a good thing we had this because, or we went over this because notice how I put the entire denominator in a bracket. Okay. The reason is because when we use our logarithmic properties here, this division sign tells me that that's going to be the numerator minus the denominator. Well, the denominator has more than one part. Okay, so that's why I have to put that negative sign through because we're going to be subtracting on both. Okay, this is a little tricky. Okay, but I feel like if you just slow down and just take your time, then you'll catch it and you're going to feel better about yourself. Okay, but anyways, let's move on. So it's going to be minus, and let's go ahead and keep this bracket here for now. It's going to be natural log of 9, and let's go ahead and put this exponent out front, so it's going to be plus x cubed natural log of e. Okay. Ready? Now I can expand. I can proceed now with expanding this left side because again we're multiplying there, so we're going to turn into addition. So we're going to say the natural log of x plus 2 plus the natural log of x minus 2. And then we're going to put a minus sign here, keep that intact, natural log of 9, and then we can just simply say plus x cubed, because we know the natural log of e, well that's just 1, right? So now I guess I'll keep that there, like this. And then I guess the last thing we have to do is just basically drop the brackets on the last two terms, and I'm going to go ahead and write all that out, or write the entire solution out again. There we go. So that was actually kind of a little tedious. I mean, but it still was a lot of moving around, right? It still wasn't too much computation. It was just a lot of moving around, right? All right, now we're going to condense again. Ooh, man, we're just doing a lot of stuff. I'm telling you, this is just moving things around, though. It's not too difficult. All right, so I'm just going to go ahead and pretty much go ahead and think this is going to be a 2-pager. So I'm just going to go and make these not so small. All right, so let's begin. Let's rewrite this. This looks like we can write log of x minus 1 raised to the 1/2 power minus log of z cubed plus the log of 5. Okay. So doing this now, it looks like we're going from left to right. Okay. So notice how when I say left to right, we have a subtraction sign here and we have an addition sign here. So moving left to right, what I'm going to do is I'm going to put this as my numerator, this is my denominator, and then this is going to be multiplied by my numerator. Okay, so hopefully you caught that. If not, I'll do it, and you'll see better, right? So this is going to be the log of x minus 1 to the 1/2 divided by z cubed plus the log of 5. Okay, so hopefully that makes a little more sense now of what I just did. And then now we have the addition sign here, so now we can essentially multiply my two arguments together. So my arguments being this and this. Well, that's easy. I'm just going to put the 5 in the numerator, aren't I? So that's just going to be the log of 5 and then x minus 1 to the 1/2 power over z cubed. Okay, so that one difficult. Let's do b. Okay, so b. We're going to go ahead and put that. Oh, wow, okay. So we're going to go ahead and put the 1 cubed. No. Oh, I know. Okay, so let's go ahead and let's put the 1 cubed out, or not 1 cubed, so 1 cubed. Put the 1 over 3 out here. We'll keep it there for right now because we're going to deal with the subtraction sign there. So it's going to be 1/3 of log base 3 of, looks like, x over y squared. Okay, so I probably should have rewrote it, but I feel like there's gonna be a lot of computation, so I didn't rewrite it by putting the 2 on top of the y squared there or on top of the y to make a y squared. But hopefully you see where I did get this, right? All I did was the log of the x is in my numerator, which you see here, and then I went ahead and put the 2 on the y and made it a y squared, and I put that in my denominator. Okay, again because this is a subtraction. Right? And of course now it becomes abundantly clear where we put that 1/3, but we'll do that here on the next step. And then that is plus log base 3 of 10. Okay. No. Yeah, let's go ahead and, I'm going to make this a little smaller so I can put it off to the right here. Log base 3 of 10. Okay, and that's going to be equal to, well, we know we can write that as now as the log base 3 of x over y squared cubed plus log base 3 of 10, and nothing's working there. 3 of 10. Okay. All right, so now we have that. All right, and then what can we do from here? Well, it looks like we can. Oh, I put a cube there. Should be a 1/3. Should be 1/3. So I'm taking the cube roots there. Okay. Anyways, so now we have the addition sign here. So that's tell me I'm going to be multiplying it. Okay. So I'm just basically going to put the 10 in front of it, right? So this just becomes the log base 3 of just 10, and let's just go and write the cube root of x over y squared. Okay, and that's it. I say that's it, but I don't know. I don't think it's too bad. We just did 3 different ones. All right. Now we're going to be solving. As this reads, remember that all logarithmic functions of the form f of x is equal to log base b of x, they are 1-to-1. Okay, in section 3.6, the alternate definition of 1-to-1 is stated that, and of course we have that alternate definition. So if we use this definition and letting, the whole point of this is saying this logarithmic property. Again, you could read that if you want, but basically what this is saying if we have, and let's look here first. If we have 2 logs and they have the exact same base, okay, then in order to solve the equation, then all you have to do is equate the 2 arguments to one another because it is a 1-to-1 function. All right, that's all that's saying. So isn't it nice how sometimes I can just break it down for you? It's my job. You're welcome. But of course, words mean little without examples, do they? So, notice how we have the exact same logs with the same bases. Okay, so apparently all we need to do is equate the arguments. Okay, now if this isn't an easy problem, I don't know what is, right? So this is just basically x is equal to 13. Okay, and of course we have to make sure that that works. We have to plug it in. Notice I don't plug in often, but when domains are restricted, I have to, right? So if I plug in at 13 minus 1 is 12, we're good to go, right? It is above 0, so that's good. So now b looks like, all right, so we're going to have to rewrite this as the natural log of x squared. That's equal to the natural log of 16. Okay, so therefore we're going to have to say x squared is equal to 16, and therefore we know x is going to be equal to, and I'm not going to write plus or minus 4 right here because I know one of these is not going to be correct. So I'm just going to go ahead and write x is equal to -4 and x is equal to +4. Okay, so I said I know one of these is not going to be correct, right? And which one is not going to be correct? Well, we know that my domain of my logs must be my logs and natural logs, right? Again, natural log is just a log with a base of e. It's just simply something saying like this, log base e, right? Instead of writing log base e, we just write natural log. Okay. We know that my domain is for all values of x that are greater than 0. That makes it pretty simple, huh? We know that x is equal to -4 is not part of the domain, right? Because I can't plug a -4 And for here, because that would not compute, would it? Not in the domain. So therefore, only the positive 4 is my solution. Now it's pretty easy. All right, so here's a good bit. I'm pretty sure that many of you do not have the change of or a calculator that you can put log base 7 into, right? Many of you probably just have a nice normal scientific, or honestly, I don't know if many graphing calculators can do it. At least they couldn't, when I was growing up. But what was I saying? Oh yeah, log base 7 is you can't do that with your calculator unless you have a really good calculator. Okay. Instead, what you have to do is you have to change the base, and you generally have to change the base into something that your calculator has, which would be the natural log or the log. Okay. So here's the change of base formula. If we have some log with some base, okay, doesn't matter what the base is, it's just some b, and then the argument is u. In order to change the base into something that we have, and in this particular case would be 10 or e, okay, then what you do is you just make it a division, right? You do the log base of your new base, the new base, which for me, I always use natural log, and for you as well, because that's the way I teach you. We're just going to use the natural log of it, okay? And we're basically going to do the natural log of, and that's it. Let's go ahead and write that out there. My elbow's touching. The natural log of u over the natural log of b. Okay, and that doesn't even look like a u, does it? It kind of does. Whatever. All right, so that's what we're going to do. We're just going to do the natural log of the argument, which is u, over the natural log of the old base, which is b. Okay, so that's what we're going to do. I'm not going to use logs, and neither are you. I mean, if you want to, you can. But I always use natural logs because, again, that's how I was taught. And of course, as we move into calculus and differential equations, you are going to be using natural logs a lot more. Okay, and I'm actually going to go ahead and snip this entire thing here because this is just calculator work. But I am going to talk about it briefly. Okay, so first of all, starting from the top. In each of the previous 4 cases, we introduce a new base. However, if we want to use the calculator to get a numerical approximation of log base 3 of 10, then it really only makes sense to change log base 3 of 10 into an expression of base 10 or base e. Okay, so notice how if we were to change log base 3 of 10, okay, we need to figure out what that is. Okay, we need to figure out what value it is. Okay, so again, if just for instance, this would be like, if it says evaluate log base 3 of 10, okay, well, you would say, okay, so 3 raised to what power will give me 10, right? Because, we did is equal to x, we said 3 raised to x power is equal to 10. All right, well, this isn't one that's nice and neat and perfect, right? We don't actually know this. We obviously know it's more than 2 and less than 3, but we don't actually know that what its solution is, okay? And therefore, we'd have to use a calculator. And again, your calculator probably can't just do log base 3 of 10. You probably can't just put that into your calculator to figure out that the number is 2.0959. So that's why we have to change the base from a base of 3 to a base of 10. Okay. So you can do that. You can use log. You see here we can use log, or we can use natural log. As I told you before, I prefer natural log. You don't have to, but for me, again, it's a habit thing because everything we do in calculus or differential equations, I just use natural logs. All right, obviously there are times using log is better, but natural log is just better to me. And of course, we see this in example 8. If we were to change this log base 9 of 200, again, we don't know what log base 9 of 200 is, right? We just know it's between 2 and 3 because 2 squared is 81. I'm sorry, 9 squared is 81, and 9 cubed is 81 times 9. All All right, so what we would do is we would write the log of the argument over the log of the old base, which is 9. And same thing over here. We could take the natural log of the argument over the natural log of the old base, and we'd get 2.4114 in both cases. And of course, we see that also in B. Okay, but again, moving forward, I will be using natural logs. And this reads, use the change of basis formula and the properties of logarithms to rewrite as a single logarithm involving base 2. Okay, so this is pretty easy, not pretty easy, but hopefully you see that the second term is already in base 2, so I don't have to do anything about that. Okay, the first one, however, is not in base 2, so I do have to do something about that. And okay. So if I want to rewrite this in a log base 2, I need to rewrite the first term with the base of 2. So I can rewrite that as a log, my new base is 2, my log base 2 of my old argument, which was x, divided by log base 2 of my old base, which is 4. That's going to be plus 3 log base 2 of y. Okay, well this is pretty easy. We see that we are, so let's go ahead and rewrite my numerator, log base 2 of x over, well, log base 2 of 4, right? Well, 2 raised to the 2 power is 2. So luckily, we can rewrite this denominator as simply the number 2. And that's going to be plus, and then we're going to go ahead and put that 3 onto the y, so we can say log base 2 of y cubed. Alrighty, and then from here, probably shouldn't have wrote so large. Let's see, maybe. Alright, so this is where some of the algebra that we have learned previously needs to come into play. We know that this is the log base 2 of x divided by 2. That is the same thing as saying 1/2 times log base 2 of x, right? I mean, because if I were to multiply 1/2 times that, I would end up getting log base 2 of x divided by 2. Same thing. Plus log base 2 of y cubed. Perfect. Alrighty, and then of course we see that 1/2 in front. Well, that can just we can put that onto my my logarithm there. And yeah, I probably shouldn't have written so large. That's fine though. Log base 2 of x to the 1/2 power plus log base 2 of y cubed. And darn it, I'm gonna have to finish up on the next page. I really just have to write the final solution here, right? I just have to combine them. Yeah, so the square root of x times y cubed. That's it. So log base 2 of the square root of x times y cubed. Okay. And again, that's just because we know we have that addition sign there, so we just multiply the two arguments together. X is 1/2 times y cubed, or the square root of x times y cubed. Okay. And I think we're off to the last one here. Yeah. All right. So last problem for the day, for the week. Okay. So this reads: use the change of base formula and the properties of logarithms to solve the following equation. All right. So we have 2 log base 3 of x is equal to log base 9 of 16. So we could change these either into a base of 9 or a base of 3. Okay. but I'm going to say it's into a base of 3 because I know that whenever I write this, a log base 3 of, 16, the argument over the old base, I know 3 squared is 9. Okay, so if that doesn't make sense, let me just go ahead and write it out. So I'm going to go ahead and keep the left side as a base of 3, L-O-G. All right, log base 3 of x squared. That's going to be equal to, and like I said, I'm going to go ahead and change the right side to a base of 3. So it's going to be log base 3 of my old argument, which is 16, over log base 3 of my old base, which is 9. Okay, so now hopefully you see what I was trying to do here. I know that log base 3 of 9, I know that's 2. Okay, so this is essentially going to look like, or at least feel like, the previous problem. Okay, so we're going to go ahead and do this log base 3 of x squared, and that's going to be equal to, all right, so I said that this is, now let's go write it out. Right, like that. Okay, so again, it's going to essentially kind of have the same feel as the previous problem, right? Where we're going to put the that 2, since it's divided by 2, we're going to say 1/2 times log base 3 of 16. Okay, so let's write that. So the left side is staying the same, nothing's changing for the left side, and it's going to be equal to 1/2 log of 16, which we know we're going to do the square root of 16, right? Because we're going to put that 1/2 onto the 16. So we're going to say log base 3 of x squared is going to be equal to the log of, and again, let's just go ahead and do the square root of 16, which would be 4. That log base 3 is 4. Okay. All right, so now we have, and let's see, let's go ahead and put this on the next page. I have 3x squared, 3, 4. Okay, so log base 3 of x squared is equal to log base 3 of 4. We know now we can just equate the two arguments together. So we're going to have x squared is equal to 4, which will be x is equal to plus or minus 2. Right? But same as before, we're not going to be using one of those, right? Because if we plugged in a positive 2 for x, well, that's okay, right? That's fine. 2 works. But the negative 2 will not work. So let's go ahead and do this like I did before. Negative 2, x equals 2, positive 2. We know that negative 2 does not work because it is not in the domain. Okay. And then the last thing is just a summary of what we did today, I believe. Yeah, summary. And I won't go over that. That's just going to be part of your notes. Okay. Anyways, that concludes today's lecture.